So let's say we've got certain flow rates. So I'll just we'll work on the sizing. So currently I'm just making a sketch of the ducting. Okay. So I'm least bothered about the sizing as such. Is the ductive got it? Randomly. So don't worry about the sizes currently. I'm just marking everything so that we'll just work randomly in this. So I'll just explain you how to work on the sizing. So the other day we had a discussion on static regain method, right? Similarly, I'll be explaining you this particular duct sizing. Okay. Always remember an elbow will be 150 mm is the internal radius we take it. Okay.
Yeah.
Okay. Let's see. Fillet. Mark the sizes later. It is just for the sketch. I'm just drawing a sketching it. So don't worry about it. So you can get sketching here. Yeah, let's say I guess that should be sufficient and probably a reducer over here. So 600 or something. Generally, each reducer length we will try to make it around 2 feet. But yeah, basically your aim target is not to make it too beveled so that your friction factor will be lesser. Okay. Yeah, so we will work on the colors. Okay. So we'll have a discussion on each color. Let's see. I'll size each and everything. So we will size it using the text as of now. See, remember shoe piece for color? Yes or no?
Yes, yes, sir.
What is the use of shoe piece? What's the use of shoe piece? Do you not remember? Hey, I asked you some question. Yes or no?
No, sir.
So shoe piece is basically to overcome the inertia of the air. Because directly if you provide it, some amount of width will be wasted because air suddenly it can't take a right turn. So when we provide a shoe piece, you're providing an initial thing because by the time airflow comes, though it will not be there, the full area you're occupying with air. We
Okay.
had this discussion. Forgot?
I think I have not attended that class. That class will be right.
Okay. So there is something
I
in
will
air
check it
distribution
in
system. We
YouTube.
had a discussion. Anyway,
Okay, I'll check that with.
check it. Fine, anyway. So let's say we've got certain airflow rate over here, mirror. Yeah. Then again, let's say, yeah, one color is over here, let's say. Virtual reducer. Then let's say we've got, so let's assume, so this is the total ducting that we have got it, for which we are working on the sizing of the equipment. Okay. So now in this particular one, you're you have something called as branches. So these ducts are called as branch ducts. This is your main duct. Okay. And these are called as collars. Understood? So whenever you design the system, you have two methods of doing it over here. One is called as velocity reduction method, and other is called as constant friction method. So we will work on both the options on the same ducting layout today. First is velocity reduction method, and second one is your constant friction method. Understood? So the rules are simple. Just a sec, let me see whether AI notes is there or not. Okay. Okay. So now we are going to work on the duct sizing. So let's say we have got dimensions over here. So I'll write the airflow rate each and everything. So 300 is next to it. So I'll make it as x6. So certain CFM. So basically what I'm trying to do is I'm trying to size the ducting. Yeah. This is the duct size. This is the duct size for this guy over here. This guy, the duct size is over here. Okay. And this is one more duct size. And then we have got a collar size. Okay. The collar size is, let's assume this is the collar that I wanted to market. And let's say each collar is individual, I mean, equivalency. So let's take, so for example, like 500 as your total airflow rate, 500 CFM for each collar as your airflow rate, right? So
Hmm.
if you take 500 cubic feet per minute as your airflow rate, so each airflow rate I'll take as 500 CFM each. So in this piece of branch dict, if you see how many collars are there after the reducer?
Two.
Two. So how much it will be? 1000 CFM, alva. So
Hmm.
this becomes 1000 CFM. Whereas this guy is how much? Four collars. So this becomes two. Isn't it? So this guy is again 1000 CFM. So here, how much it will become totally? 2000 plus 1000, 3000, 3000 plus again 2, I've got it. So I can make it as 4000 CFM. Sorry,
Hmm.
2000 plus
Two
3000
thousand.
plus 1000, that's 4000 CFM, right? And then we have
Yes.
other two more that will basically cost 5000 CFM. The total ducting will should be designed for 5000 CFM. So the total airflow rate is this one. So 5,000, 4,000, and then again I've got 2,000 one side and 1,000 on one side. So now I have to do duct sizing for these things. Am I clear?
Yeah.
Now, we have to understand the site conditions before designing a ducting. That means with whatever duct size you want, you can't do it at many cases because what will happen, there is something called as the bottom of the beam and bottom of the false ceiling. So, between the beam and false ceiling, whatever height is remaining, according to that, you have to decide the maximum height of the duct. I'll just give an example. Let's say I've got a place where bottom of the duct is, for example, say bottom of the slab. Let's say bottom of the slab is, let's say, some 14 feet or something. Okay. So 14 divided by 3.28. The reason why I'm doing it is this is in meters, Alva. That's the reason. So it's 4.26 meters, 4,260 mm. So this is your bottom of the slab, let's say. Okay. So this is bottom of the slab. And now out of the slab, let's say, we have got a beam of, for example, some 600 mm, 2 feet beam, 2 feet beam, I've got it. Now, let's say I wanted to have a 9 feet or anything as my false ceiling. 9 divided by 3.28 is how much? It will be 2.74 meters. Let's say 2800 mm I wanted to have a false ceiling of. So this is my false ceiling. So at multiple locations, when I have a beam, everywhere I can't take offsets at all. And not only that, space availability is also important, right? So now, what is my active space that's available? Because this is below false ceiling space. So what is the active space that's so this X mark is bottom of like a room space below the false ceiling, and the hatched one is a beam. So now, don't you think the remaining space that I've got it is only this gate, which is around 860 mm or not?
Mm.
Yes.
Yes.
But in this 860 also, the following thing, of course, generally you don't get this much heights anyways. I've just randomly said some 15 feet, but generally you get around 3 meters or 3.2 meters. If you get, you are lucky in most of the practical cases. Okay. So if you consider those things also, like practically, but anyway, I'll tell you the, like, what is the space that's available. So when you consider this 860 mm, when you wanted to do a beam, can you utilize entire 860 mm? Probably not, because if you remember,
No.
there is something called as a duct joint.
Mm.
When there's a beam, like, you have a TDF flanges around, right? In air distribution system, you guys remember the type of duct joints. The
Yes.
first
Yes.
or the generic one that we use it in factory is basically using TDF joint where we have a flanges around a ducting. You guys remember it or not?
Mm.
So if you take a ducting, around whatever duct you take, almost 32 mm, the flange will be there. 32 mm. The thickness of the flange is 32 mm. Please remember this data. Okay. This will be around 32 mm. You have a flange, right? And then along with the duct, you will be thermally insulating it.
Very universal
Yeah.
standard.
Which one? Yeah, the 32 mm is the universal standard. At least in India, all fabricators, we have this 32 mm.
Okay.
That's MACNA norms. So throughout the world, it should be the same anyway. So we have an insulation of 9 mm thickness minimum we'll do. 9 mm depends again on the consultant and the length of the ducting, but then length is very large. You don't want to lose heat means then you might even go for 13 mm. But yeah, most of the cases we go for 9 mm thickness for ducting. So let's say offset 9 mm, it'll go for the insulation. So when you do for smaller projects, okay, you can avoid it's not possible in all the projects. So it's better we even consider that as well, flanges, because you can always ask me wherever the beam is there, I'll not keep a flange. Yes, to some extent. But how much you're going to save? Only 132. Other 32 you can't because anyway you've got a false ceiling. You agree? And
Mm.
you have certain false ceiling thickness as well.
Yeah.
Say if it's generally made with the 25 mm gypsum, but for gypsum you require channel supports or something.
Yes. Yes.
So channel support generally it will be around 50 mm. Because generally the sections that we're going to use
Mm.
is like 25 by 50 mm like that. So offset 12.5 is your thickness of your gypsum board, 12 mm or 12.5 mm, and then again you've got 50 mm as your channel, let's say. So how much is available in this? The availability is 979.99 sorry 797.5 mm, but in that again I have to remove 32. You agree? So if I do this calculation, 797 minus 64, 32 plus 32,
Mm.
64 is 733. 733 minus 16 mm. So it will be around 217 mm is what you will be losing it. Sorry, 717 mm is only space that's available, considering your duct flanges. Understood? Am I clear?
Mm-hmm.
717 mm. But at the same time, if you have any pipes or anything that's crossing, worst case, you have to consider even that as well in your mind. Let's say some pipe or anything is crossing it elsewhere. Of course, we'll make sure that it's not at the beam location, so somehow we can manage. But anyway, worst case that you get is 700 mm. Understood or not?
Mm.
Of course, the duct supports, everything will be there, but that's a part of in like because wherever you have a flange, you're not going to have your duct support, right? So you will have your duct support at this location. Wherever there is no flange at that location, you can have your duct support. And then you can have your threaded rod. Understood?
Mm.
So that can again count it up to 50 mm like that also. It's better you take some safety. So whatever available space is there, you have to evaluate and then decide what is the maximum height that's available for you. Understood or not?
Okay.
Clear?
Mm.
So generally what we do is whatever the bottom of the beam we get it. So minus 100 mm if we do it, will be safer. Clear? 100 to
Okay.
120 mm if you remove it, you'll be safer that way. Clear? Now,
Okay.
whatever the bottom of the false ceiling is there, okay, whatever the bottom of the false ceiling you have it, bottom of the false ceiling is 860. But what we could use is roughly 860 minus 150 if you take it, that will be 710. So 700 mm is the maximum height of the duct that I can use it in this project. And you're lucky if you get these dimensions. Generally, we don't get this much anyway, most of the practical cases. Clear?
Okay.
Okay. Now we are going to go for the next one, which is basically designing your ducting. So first, I'm going to explain something called as your velocity reduction method. We are going to have a discussion on velocity reduction method. First method is velocity reduction method. Velocity reduction method. Sorry. You guys are comfortable on laptop, right? Instead of iPad.
Yeah. Yeah. Laptop is better.
Yeah, so I'll be explaining on this velocity reduction method. So when you consider velocity reduction method, you have to understand the following things. So you have to follow certain velocity equations, which I'll be explaining you, the velocity standards, I should say. So in this, the first one is your branch, your main duct, whose velocity will be 1000 to 1200 to 1500, see 1200 FPM, feet per minute to 1500 FPM. Understood? Feet per minute. Clear? Duct. Clear? But whereas if you consider your branch duct, the velocity will be somewhere between a 900 to 1200 or even 800 to 1200. 800 FPM to 1200 FPM we take it. And then you have collars, which will be somewhere between 500. I mean, need not be 500, it could be 350 also, depends on the distances. But say generally we say around the 350 FPM to 750 FPM max. So you design using this particular velocities. You design your ducting considering this. At the same time, the name itself it says is reduction. That means compared to one first duct, your second duct velocity should slightly reduce at least by 50 FPM. Understood? So this one more rule is you have to, these are the following rules that you have to follow. The first rule is your after every reducer after every reducer, make sure that the velocity is reduced. Velocity is reduced by 50 FPM, 50 to 100 FPM at least. FPM, comma, friction factor we should not be more than zero point 0.1 inch. Friction factor should not be more than 0.1 inch per 100 feet. Understood? So these are the rules that you have to follow while working on this particular velocity detection method. Understood or not?
Okay.
With your main duct. Let's say the first is your main duct. So main duct is 1200 to 1500 FPM I can use. At the same time, a friction factor should not be more than zero point 0.1. So first, I'll work on this duct sizing tool. Okay, this tool I'll be sharing it with you guys. It's quite simple. So you will basically decide what is the temperature of your air. Let's say somewhere around 55 or 97% RH. The reason why we consider this is generally your temperature of your air will be like, your coil temperature is 3 degrees, so your grill temperature will be somewhere around 12 degrees. And it has already dehumidified itself. That means it's nearly equivalent to 100% RH or not? Because whatever additional moisture content is there, that will be left over the coil. You agree?
Okay.
If you remember psychometrics, air will have certain amount of moisture content. Then its capacity will reduce if you cool it down. So when you pass it over your evaporator coil, don't you think your temperature will reduce?
Yeah, it will reduce.
It will reduce. So when the temperature reduces, your moisture holding capacity also will decrease. So whatever the remaining moisture is there, it will come in form of drain. So remaining air, whatever is there, don't you think it's already saturated?
Okay.
Unless you give heat, it will not be able to take more moisture content. You agree?
Mm, okay.
So for that reason, it's like, it's saturated. So I'll consider 55 degrees Fahrenheit with 97% RH. Now coming to the next one that we have is flow rate. So here the flow rate is 5000 CFM and head loss, let's say is head loss will not worry. Instead, we use velocity method in this case. So if we use velocity method, you have to check your velocity column. So in the velocity column, now the velocity I'll initially take 1500 FPM. So here the head loss is crossing beyond 0.11 or not? 0.1 or not?
Yes, yes, yes.
So can I use this velocity?
No, it has to be
So I'll
reduced.
reduce it to 1400 and I'll see. Yes, 1400 is fine. So 1450 also. So 1450 also is 1400 velocity I'll take. So the friction factor is how much? 0.98 inches per every 100 feet. You agree?
Mm.
Now the maximum height that's available is 700 in this case. So 700 means how many inches is it? 700 divided by 25. So that's 28 inches. So maximum height I can go is 28 inches. So my width of the duct is 20 inches. Height is 28. So instead of this, don't you think it's better if I make it kind of a square duct
Mm.
so that my aspect ratio will be cool? So I'll try to make it square duct in this case. Let's say it's 22 inches. 24. Yeah, 24 by 24 is square duct almost. Or I can even, because here 1 inch it's giving extra. So I can go for 22 by, uh, yeah, 22 by 26 inches. So width, I wanted to make it as 26 inches. Height, I wanted to create 22 inches. Is it okay?
Okay.
But anyway, this is like rare applications you get this much height. Generally, like, if you get 1.5 feet, you're more than happy. Okay, practically it won't be like the heights I've provided it in the example. Practically, when we do in this project, then you'll understand the problems. Anyway, so this is 26 inches and this is 22 inches. So 26 into 25 is 650. So definitely this duct could be 650 by what is the width of the height of the duct is 22. 22 is how many inches? 22 into 25. 1 inch is 25.4. So we'll take roughly 20, 25. So that's 550 mm. So that width is 550 mm, 5000 CFM, and velocity is how much? 1400 FPM. FPM. And what is the friction factor we got? 0.09,
0.09.
0.098 inch per 100 feet. Understood?
Mm.
Now coming to the next one. Next one is how much CFM? 4000 CFM alpha. So I'll write it as 4000 CFM. So if you take it as 4000 CFM, then automatically my friction factor is way high. That's 0.112. Now, don't you think you have to reduce anyway? So
Mm.
let's say I'll make it as 1300. So I can make it as 1300 or 30 because I want to reduce it by 100 FPM as per rule. So I'll consider this. So in this case now, how much is it? 22 by 22.
102.
So how much will it be?
Mm.
22 by 22 in the sense. So 22 is 500 by, just a second.
500.
22 into
500.
20, 25 is 550 pa. Sorry, my mistake. So I was thinking because 20 inches is 500. This is, I've written it wrong, but anyway, it's 500. So now what I have to do? I have to write it as 550 by 550. You agree? Now coming to the next one is we have to do sizing for this branch and this branch. We agree for 1000 CFM and 2000 CFM. So for 1000 CFM, let's make or for 2000 CFM, let's make for 2000 CFM, I'll mark it over here. So here I have to reduce the velocity lesser than 1000. So I'll start with 1000 FPM. Not even 1200, 1000 will be safer. Let's say 800 to 1000 FPM, but it's not mandatory also because we generally use constant friction method. Anyway, so 1000 FPM if you do it, what is this duct size I got? 14 inches, right? Yes or no? For
Mm.
22 inches, the width of the duct is 14 inches. You agree?
Yeah, yeah.
Yeah, or else I can consider 1100 as well. But generally we try to avoid it. But anyway, so 1100 also seems fine. But yeah, 1000 is better. Anyway, 0.06. So that's 14 inches. So 14 is how much? 14 into 25 is 350 mm. So this duct size is 350 by how much is the duct size? 550 mm. You agree?
550.
550. And then we have got the next one, which is your 1000 CFM. 1000 CFM if we take it. So this is again 1000 means again the velocity will be friction factor is crossing beyond. So don't you think you have to reduce it by 900 or something?
Mm.
950 FPM or
Mm.
something? Yeah,
Yeah.
950 FPM seems fine. Or to be safer, I'll consider 900 FPM. So at least 8 inches. So the duct size is 8 inches. So what is 8 inches is how much? 200. 200 by 350, 550. You agree? This is the duct size that we have got it. Understood or not? So I've maintained this is constant. But if you want, you can again use a transition piece, or you can use you can use a transition, you can use a reducer or increaser even to change this, size of the duct. You agree? Because this 200 by 50 is very awkward. Yes or no?
Mm.
So we have to design it using, anyway, let me complete collar size also. Then using this dimension, we will draft it. Is it okay? This is like 350 plus 200 is how much? 550 exactly. Anyway, yeah, that's luckily it's fine. Same, we got it. So that's fine. So anyway, the last one that we have is this collar sizing. So this collar, don't you think I can change this collar size? I have to size this collar. So the collar, each one is 500 CFM and velocity. What is the velocity of the collar? How much it can be? 350 to 750. Generally, we
350
take an average of
750.
500 FPM. We'll take a value of 500 FPM. Then let's say the height of the collar is 6 inches height. So it is 30 inches. Uh, 30 into 25 is 750. So it is 750 by 150. So this is the collar. See, except for collar rest all, we should make sure that our aspect ratio is not worse than 1:4. Understood or not? Except collar for rest all area because
Mm.
collar length is very less, so sagging and all will not be a problem. At the same time, we have a grills or collars, so that will ensure that the sagging doesn't happen. So except for collars for rest all locations, you to make sure that your your aspect ratio is not worse than 1:4. You can see anywhere. See, worst case here I could get is 550 by 200. So 200 into 4 is how much? 800. So I can go up to 800, but still we have stopped with 550 mm. Understood or not?
Mm.
Okay, so this is how you basically work on velocity reduction method. So now shall we go for constant friction method?
Okay.
Right? So in constant friction method, the next method is constant friction method, which we generally use most of the cases. Constant friction method, your main duct velocity will not be only one rule is two rules we follow. One is uh, your main duct basically is max velocity. Max velocity for comfort application is 1500 fpm. Of course, if in industrial where sound is not really a problem, you can even go for up to 2000, 2500 as well, no problem. But for comfort applications, you will take only 1500 fpm is the largest. And then your collar sizes, whatever you have it, collars, you will always use velocities. The reason is collars is one important aspect where it is just near the grill. If the velocity is very high, you will get air cutting noise from the grill blades. Understood? Because whenever you've got a collar, through this collar, you will have a grill. I'll just show you and try to show you HPC collars. Just a second. Collar, just with the grill, with the grill. Right images. Anyway, these are the grills. If you remember, I'll explain you this. So inside the collar, you will directly have, okay, not right image isn't coming anyway. So to the duct, you will directly tap off this particular grill along with the, yeah, you can see it over here. I mean, it's not exactly, they made it with circular one, but anyway, like this to the collar, you will fit the grill. And this is the worst part. You can't have a circular duct. This is a really shitty one. But anyway, so to the collar, you will basically fit a grill. So because of this, is the aspect ratio is a bit higher also, no problem, because this grill is there to make sure that the duct won't bend. And along with the backside, you have this collar damper as well. So if you see the section, this section will be grill, and then you have got a collar damper here, where you will be able to control your like airflow amount. You remember collar damper?
To control
Explained
air.
to during air
Yes.
distribution system.
Yeah, that flipping air.
Yeah,
Control.
so to control the air, it's like a volume control
Mm.
damper, but only for the collar that we use it. Understood?
Mm.
So for that reason, understood. So now that particular one, we have to use this velocity method only. But whereas your like friction maximum factor should not be more than 0.1 inch per 100 feet. These are the only conditions that you follow for constant friction method. Sorry. Constant reduction friction method. Yeah. So when you consider this constant friction method, so here we'll redesign the sizing. We'll reshape the sizing using this. I'll try to maintain the same height anyway. So what is it? 5000 CFM alpha. First one is 5000 CFM. Head loss is zero point 0.1 anyway. 0.1. So it is 22 inches. 22 inches means 25. So 26. 26 into 25 is again 650. So this is same again.
Mm.
Velocity is 1400, 1408. That's fine. And then coming to the next one is 4000 fpm. 4000 fpm is 22 means it is 21 means obviously you have to use 22. So this is also fine. 22
Mm.
inches.
Yeah.
Then coming to this one is 1000 CFM if we take it. Sorry, here we didn't size it because obviously this 1000 CFM and this will be same. So we can use the same size obviously. And size it previously, but anyway. So 4000 CFM. So if we take this 4000 CFM, it's fine. Then it will be 2000 CFM. So if you take 2000 CFM, zero point 0.1, this is 13 inches. 14 inches we can take.
Mm.
So that is again same almost 350 by 550.
Mm.
And then coming to the last one is 1000 FPM. So we'll take this 1000 CFM, 1000 FPM, sorry, with 1000 CFM and zero point 0.1 we'll take it. And this is around 8 inches we got it, which is again same 200 by 550. You agree?
Yeah.
So plus or minus, you will get one size because when we design also, we'll try to make sure we have around like, zero point 0.1 as a friction. But this value will change when you use like, very high velocity. So when you use high velocity at that time, when the your velocity is more than 1500, then you try to maintain as around you will change the uh, friction factor. Understood? For example, because say for example I've got 10,000 CFM, let's say instead of 5,000 I've got 10,000 CFM. Point one, if you do it, what is the FPM that is there? 1600. Can I have 1600 for comfort application?
Mm.
What is the
No,
maximum
no.
velocity? What
13,
is the maximum velocity I can have?
13,500.
I clearly told you maximum duct velocity that in the main duct I can have is 1500 FPM, right?
15, 15, that is 15.
Yeah, 1500 FPM.
Mm.
Then automatically your friction factor itself is less 0.077. Understood?
Mm.
So like that, you have to design. So it's simple. Both are simple. Only thing is in one method, you'll keep velocity as your concentration. In the second method, you'll use your friction as your concentration. Almost you'll get plus or minus same sizes if you do reasonably fine. Understood?
Okay. Yeah.
Clear till now?
Okay.
Okay. Now we'll practically draft this drawing, let's say. Because randomly I've drawn it. So now we will see. So generally how we do is basically, let's say this is, we'll change the sizes. 200 by 550 is stupid. So I'll change the size after this after it is. So I'll just show you how it's done. So first done is I'll split the screen if you're comfortable.
Mm.
Yeah.
Yeah.
This is one. So then, mhm. What is a split screen? Huh? It's not coming to my mind today. But anyway, we'll try to design it using this.
That AutoCAD is split also.
So yeah,
Split
suddenly
screen.
forgot the name. Not split screen.
Viewport,
You
viewport,
have
viewport,
a
viewport.
v. Report. Yeah, sorry. Suddenly forgot. Right. So then this particular one, we'll take it with 650 just to see. So this is your 650. Let's say I've got a collar. What is the size of the collar? 750 by 150 Alva.
Mm.
So I'll take a particular one offset 750 mm, offset 100. So this is how you design your collar. Let me put that done. Polyline. Yeah, this is done. So let's say I wanted to make square extra. Yeah, this is the collar. So then I've got one more collar, mirror. Yeah, so we'll just shift it over here somewhere. Okay, and then we'll go for a reducer. Depends on the site condition, you'll use the sizes. Trim, be done. And length of your reducer should be 600 mm as I've told you. Okay, not mandatory for 600, but yeah, if the size change is very less, then you need not even use 600 as well. So length again, I'll make 550, offset 550 by 2. So that's again this one. So in this case, I can even go for 450 mm reducer as well. But general practice is we'll keep 600 as a length of your reducer. But the size is anyway. The size itself has reduced to. Yeah. If there's velocity, friction, everything you'll not mark. You'll just give velocity. That's all. Okay. So here, what is the duct size? It is the duct size is 4000 CFM alva. So this is 4000 CFM, and this is 550 by 550. Then you have again couple of collars, right? Whenever it's an open ducting, you try to maintain same level for collar. You'll extend the collar so that everything will be in line. But that's aesthetical decision. That's all, nothing technical in it, obviously. Then I wanted to use a reducer. So here I'll take a ducting. Here I'll take a ducting. Let's say. Now what is the velocity? This is 1000 200, right? Offset 200. And this side is how much? Offset is 350. Offset is 350. Fillet radius 150. Fillet radius 150. Same size. Right. Then it is the size is how much? Offset 200. Offset 200. Sorry. Offset 200. I got it over here. Offset 350 alva. Yeah. So luckily this 200 plus 350 is same, else this will be a trouble. Anyway, practically when we do it, you'll get other options. Match properties. I'll match it over here. So this is minus thing, and then we've got the next one, which is this particular one, which is 350 by 550, 350 by 550, and then that is 2000 CFM. You agree? Now, what I would like to do is here, 250 by 550 aspect ratio is really worse. So, I mean, width is right, so I can even make it as a square, right? So, for example, if 1000 CFM, I use constant friction method, 0.1, and let's say I have my duct size as, say, for example, instead of 22, I wanted to make it as, say, 12 inches or 14 inches. So I'll take it as like, height as 14 inches and width is 12 inches. So what I'll do is trim, yeah, T, done. This is this size over here. Then I'll take again 600 or anything, or 450 is also fine. Yeah, or 600 I'll take it. And one side I'll use it. This I'll make it as your single side reducer just to show, because double side we had this over here. Now let's check. I wanted to have, what is the size that I have it now? 12, 30, 300. So offset 300. I'll take it. Extend. The size is how much now? 300 by 300 by 350. 350. Yeah. So this is your duct size. I got it. So from there, I'll basically this is your 1000 CFM. So you made it like this. So similarly here, 350 by 550. Let me keep it like that. So I'll take and I'll obviously use this colors. Right. Copy. These are the directions, let's say, and then we've got roughly this one over here. I've used one color over here because of the side conditions. Let's take from here. I wanted to have, I want to keep everything the same line. Yeah. Stretch it up, and then I'll take one more line. Yeah. That's 150. What is the size? 350 alva. Offset 350. Length. And then again offset 350. Done. And then we have got, I have one more color right here. Rotate. Mirror. Here there's a small error because this is the direction of the flow. Don't you think so? Yes, I'll
Shoe
change
piece to
the
be.
arrow size. Yeah, that's what. So 150 mm. Okay, so it's very close. So don't you think this is the direction? So can this should be correct? No,
Shoe
right?
piece to be mirrored.
So I have to make it mirror like this. So yeah. So here I made it like this. So I've made, let's say, one more color over here, and then I've got a ducting. Offset 600. Now what is the length I've got it? Now I wanted to use directly this size, 300 by 350. Right. So I can make it as 300 by 350 offset, 150 on the other side. So here I'll make it over here, which is how much? 300 by 350. 300 by 300 by 350. And this is 1000 cc. Understood. And then let's say I've got a collar. I've got two more collars over here. Copy, copy. The collar is over this side right here. Copy. And then over here. With this, we made the ducting. Understood or not? At the same time, don't you think you have to use a volume control damper? Yes or no? So I'll place a volume control damper. So I have standard blocks. Obviously, you can make it as well. Data, design jobs, standard blocks. Sorry, standard blocks. And I'll take to BCD over here. So these are the standard blocks I'm using it. That's it. Yeah. So this is a block I've used it, and one more block that I wanted to use it is this one. So these are the two blocks that I've got it. Understood. So do you think here I require a BCD? Yes or no?
Yeah.
So
Both the
using
side.
this, you have designed the ducting using both the methods. One is constant friction method and velocity reduction method. Clear?
Mm. Okay.
Understood?
Yes.
So this is how you basically work on your duct sizing, and this is how you basically draft a duct. Am I clear?
Mm. Okay.
Okay. So this is nothing but your concept of duct sizing. And then one more thing that is left is basically your plenum sizing. Your plenum size should be in such a way that your phase velocity will be as less as possible. Okay. So when do you use plenum? When do you use plenum? Tell me.
Mhm.
When you wanted to have multiple ducts to a single unit or multiple units common from a common duct supply, or two units are supplying airflow rate to a single ducting system. Let's say it's 24 by 7 application or something. You agree?
Okay. This one,
I'll
like
I'll
air
just give an example.
conditioning.
Let's say,
This one.
yeah, I'll just give an example over here.
Mm.
I'll take AHU something. Let's say I've got a ceiling system at AHU 5000 CFM each. Let's say I've got one AHU 5000 CFM and other AHU 5000 CFM. Okay. Now for these both ducts, let's say I've got a effort. And this is my ducting I've got it. So here I've gone for clean. Obviously, I should leave some space for my NRD and all. Don't worry. Offset. I'll take it like this. Extend. Yeah. So let's say this is my complete setup of the ducting. So when you take it, here I wanted to place a duct. Here also I wanted to place a duct. And here to here also, we'll try to take it over here. So when you take it here, you have a NRD, and here also you'll have a NRD, obviously. What is the use of NRD non-return damper?
One, if you one thing is running, then other duct will be closed.
Yeah, obviously. So when this particular is on, you don't want air to come through and bypass it. So for that reason, you will use a NRD, which we had a discussion previously. So you'll obviously place a NRD as well. So I'm just marking it here. So this, let's say, is your NRD. Okay. Now, when you have it, this is your phase. See, what are the phases? So this is supply phase. This is your return. Your like this is your supply. This is also your supply. So here, the velocity of this area, this face area, the highlighted area or highlighted line, whatever the surface area is there, that should be in such a way that the velocity should be as minimal as possible. I mean, somewhere around below 800, definitely you will maintain. So here, what is the length you've got it? 5 meters. You agree?
580.
5,000, so I can even reduce it probably by the 500 mm, let's say. Okay, 500 is kind of a tough job, but that's okay. Yeah, I've maintained it like this. Now let's say this is your how much is that? 4,583. So 83 mm, we can definitely reduce it to round it off, right? So around this dimension is this plenum will be mouth, let's say is 500 mm or 400 mm mouthpiece height. So let's say this duct size is 4,500 by what is the height of 650 duct means? Don't you think at least I should have 700 as my duct height or not? Yes or no?
Okay. Yeah, 500. Deduction by
Yeah.
500.
And this is 1063 because randomly we have run it. But anyway, so let's say 63 mm I wanted to reduce it. So this is 1,000. So 1,000 by 700 by 700 is a depth anyway. 1,000 by 4,500. This is my plenum size. You agree? Now, for this, for 5,000 CFM, let's see what is the phase velocity over here. So, what is the phase at this point? Don't you think this is 4,500 by 700 is a phase or not?
Hmm.
Phase area, phase dimensions are how much? 4,500 by
1000.
4,500 by
1000.
1,000 mm. So, if you take this 4,500 by 1,000 mm and the CFM is 5,000, Ashya, because each AH is 5,000. So, obviously, this duct is designed only for one working, one standby. So in this case, let's check what is the size, what is the value that I put it. So value is 5,000 CFM. Uh, this height is how much? 1,000, sorry, not 1,000,
700.
700 alva.
700.
This
Hmm.
is 700. Yeah, this is 700. So 700 divided by 25, if you do it, then it's 28 inches. So let's check this is around 28 inches and 4,500, right? 4,500 divided by 25 in inches I wanted. So it should be 180 inches. 180 inches means your velocity will be lesser than 500. 200 velocity, not, yeah, even lesser than 200. So you are much safer only. You agree?
Hmm.
The reason why bigger is better or velocity why it should be lesser than 500, the reason why we do it is basically the plenum works on a simple principle. Okay. So when these AHUs have very high velocities, both are connected into a single plenum. If the velocity is very less, what will happen? You will have a lot of turbulence. And second thing is, it will not be transmitted because you will have a lot of velocity losses because of this turnings and when the duct hits them. You agree? But whereas when your velocity is reduced, so initially you might have, see, once it starts pumping, it will hit this surface, I agree. But then if your velocity is reduced, slowly the air will completely occupy this one. And then
Yeah.
your complete velocity energy will be converted into your pressure energy. Your kinetic energy is converted into potential energy, the pressure energy.
Russian.
So
Hmm.
when you have this pressure energy, so now what will happen? You're pressurizing the plenum. But here it's atmospheric air in the collar. Because of the
Hmm.
pressure difference between this pressure in the plenum and this one, air will flow smoothly. So whenever you design plenum, your main objective is to convert maximum kinetic energy into pressure energy. So what should you do? You have to reduce the velocity for that. Understood or not?
Okay.
Am I clear?
Yeah.
So like that, you have to always work on the duct sizing. Clear? So this is a short note on your duct sizing. So on the previous session, we had a discussion on static regain method. Today we had a discussion on both velocity reduction method and constant friction method. Clear?
Okay.
Tomorrow, what we'll be doing is we will be practically working on our project. We have got our heat load sheet, right? Heat load
Yeah.
calculations. So in that, we'll select certain type of deductible split AC or anything, and then for that, we'll work on the duct design. Then I'll give you an assignment after that where I expect you guys to work. I mean, both of you guys have access to AutoCAD. Mohammed didn't join today, right?
No.
You have AutoCAD access, or how is it?
Presently, you don't have access.
Okay, you do one thing, you try to sketch it and then you try to make it on pen and paper. I guess that should also be fine on roughly to
Okay.
calculate it.
Okay. Okay.
Make it with a single line also, I'm cool with it, but I want you to work on the duct sizing practically
Mm,
once.
mhm.
Okay,
Okay.
fine. So we will be connecting again tomorrow for understanding this duct sizing. So once after that is done, then I'll be teaching you on BOQ, how to arrive the quantity of ducting using formulas.
Okay.
Good enough?
Okay. Yeah.
Okay. So this is nothing but your duct sizing that we have learned today on particular one. So you have got any queries on today's session?
Not that it is clear.
Yeah. ठीक है. What about you, Vinod?
Okay, clear.
Yeah.
Yeah, yeah.
Okay. Okay, man. Then tomorrow we'll connect back. We'll start again. It's hardly like 15 minutes we've got. So yeah, we
Okay.
can connect tomorrow again.
Yes.
Okay. Fine. Fine.
Yes.